Hi everyone, this is Professor Mayungar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. Hello guys, today I'm going to show finite element analysis of a step shaft subjected to torques at different locations. Let us see the statement of the problem. A step shaft is subjected to a torque as shown in figure. Determine the angle of twist at the free end and also twist in each section of the beam in degrees, and also find the maximum shear stress in each step. And we're considering in this case Young's modulus is 208 gigapascal and Poisson's ratio is 0.3. So it is evident that it is a step shaft fixed at the left hand side, and we're having different types of beams. First shaft is hollow one, which is having outer diameter as 100 mm and inner one is 80 mm. Similarly, the second one, it is a solid shaft of diameter 80 mm, and at extreme right hand side we are having a solid shaft of diameter 60 mm, and we are providing different types of torques at different locations. At B, we are providing a torque of 3 kN in anti-clockwise direction, it will be positive, and again at C we are providing a torque of 2 kN in clockwise direction, it will be negative, and at location D we are providing another torque of 1 kN in anti-clockwise direction, so it will be positive. Right, so in our case we have to find out the angular twist of the free end, and also we need to find out the twist of each of the different sections in degrees. By the same time we need to find out shear stress for each of the sections. Another thing is we can follow two different methods to have these results. If we are considering a beam, in that case we'll get all the results excluding that shear stress, and to have shear stress we need to follow a different element type, right? So without wasting time, let us start our analysis using ANSYS Mechanical APDL. Right, first of all we need to create a directory, and in that directory we need to save everything. Next to that we can change the title of this one from file and change title. We can name this one as FA14. To see the title, plot replot, it will show the title at the lower left corner. Next one, we need to define what type of analysis it is, and it will come from preferences. It is a static structural analysis. Okay, next to that we need to define elemental properties, and it will come from preprocessor. Element type, add, edit, delete. As I told earlier that we can consider two different types of elements. We can consider beam or pipe. If we are considering beam, in that case we'll get all the results excluding the shear stress. For shear stress we need to follow the pipe element. Right, let us follow both the techniques. First one will follow beam with 3 different strain, and element type reference number is 1. Close it. Next to that we need to select material properties, material models, structural, linear, elastic and isotropic. And in this case we are having modulus of elasticity as 2.08 into 10 to the 11 Newton per meter square, and Poisson's ratio 0.3. right, so modulus of elasticity is 2.08 E11 and Poisson's ratio is 0.3. okay, let us close it. Now we need to provide sections, beam, common sections. Actually it is having step shaft of 3 different cross sections. First section is having ID1, and we are keeping the name of this one as hollow. It is having outer diameter 100 mm and inner diameter is actually 80 mm. So external radius will be 50 mm and internal radius will be 40 mm. Right, we can change the unit to meter. So external radius is 0.05 meter and internal one is 0.04 meter. Apply. Now second ID, we can name this one as middle. It is a solid one, so change the subtype to solid one, and it is having radius of 0.04 meter. Apply. And the third one is also solid one, so ID number is 3, and we are keeping the name of this one as end, and subtype again it will be solid circular shaft of radius is equal to 0.03 meter. Okay, we have defined all the different cross sections of the step shaft. Right, next to that we need to start modeling. Let us see the question again. So we need to create 4 different nodes. First node will be created at origin, second one will be at a distance of 0.3 meter, third one will be at a distance of 0.7 meter, and fourth one will be at a distance of 1.2 meter from origin. Right, so modeling, create, directly will create nodes. So create nodes in active coordinate system. First node will be created at origin, so apply. First node is already made. Second node will be created at a distance of 0.3 meter from origin, so 0.3. Apply. Next one will be at a distance of 0.7 meter from origin. Apply. And last one will be at a distance of 1.2 meter from origin, so 1.2. okay, we have created 4 different nodes, and all these different nodes should be connected in the form of elements. Right, so create elements, and as it is a step shaft of different cross sections, so we need to define the element attributes before joining in the form of elements. Right, so element attributes, and you can see first section is actually hollow, so auto number through nodes, you can join node 1 and 2. okay, done. Now next one, node 2 and 3, it will be having different cross sections, so element attributes, and from section number it will be middle one. Okay, now we can join these two nodes through nodes, node number 2 and node number 3 join together. Okay, done. Again we need to see element attributes and change the section. The last section is the end one. Okay, now we can join these two through nodes, node 3 and node 4 joined together. Okay, so our model is ready. So we need not make any kind of meshing because already we created nodes, so meshing is not required, right? Now we need to apply our boundary conditions from loads, right? Analysis type, it is a new analysis and it is a static structural analysis. Okay, so define loads, apply structural displacement on nodes. So let us select the extreme left hand side node or node number 1. Okay, selected all degrees of freedom with 0 displacement, that means node 1 will be fixed. Done. Now we need to apply load at different locations, that means we need to apply moment at different nodes, right? So define loads, apply structural force moment on nodes. At second node we need to apply a moment of 3000 Newton meter. Let us see the question again. At location B we need to apply a moment of 3000 Newton meter in anti-clockwise direction, so it will be positive 1. Second one, at location C we need to apply a moment of 2000 Newton meter in clockwise direction, so it will be negative. And at location D we need to apply a moment of 1000 Newton meter again in anti-clockwise direction, so it will be positive 1. So we are applying moment of 3000, 2000 and 1000 at B, C and D with different directions, right? Okay, so let us select node number 2, apply. It will be 3000 Newton in anti-clockwise direction, so it will be positive 1 along MX. Apply. First one is made. Now let us select the third node, apply. In this case it will be in anti-clockwise direction, so it will be minus 2000 Newton. Apply. And again the last one, node number 4, selected. Okay, it will be 1000 Newton in anti-clockwise direction, so it will be positive. Okay, so we have defined all the moments at different locations. Now we need to solve it, right? So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. We can see our results from general post processing, right? Let us close it. General post processing, read results from last set, and we need to define the element table, define table. Another thing is, for seeing the torsional moments of the step shaft, we need to depend on different numbers. It will be SMS 4 and SMS 17, right? So let us add it, and from drop down menu we can select by sequence number, and it will be SMS 4. Apply. Again repeat the process by sequence number, and it will be SMS 17. Okay, we have selected two numbers, SMS 4 and SMS 17. These two numbers will be representing actually torsional moments of the step shaft at different locations, right? Let us close it. And first of all, we want to see results from listing. So list results, and we want to see reaction solution first and all items. This is very important results. You can see the reaction forces at node number 1. We can see the forces developed at node 1 along X, Y and Z. Also we can see the moments also developed at X, Y and Z, right? Next one, we'll see the rotation of the beam at different locations. So it will be nodal solution, DOF solution, and we want to see rotational vector sum, right? It is showing that at node number 1, it is having 0 rotation along X, Y, Z, and node number 2 also having different values, and maximum rotation is occurring at node number 4. It is 0.4973 into 10 to the minus 2 radians. So all these values actually we are getting in radians, that to be converted into degrees. These are actually rotational values of different sections or different nodes. We are having total 4 nodes. At node 1 we are having 0 rotation, and at node 4 we are having maximum rotation of 0.4973 into 10 to the minus 2 radians, right? Let us close this one. To find shear stress for each elements, we can see from elemental solution, and it will be stress values, and we want to see shear stress in XY direction. Okay, so these are representing shear stress at different sections, and we can find stresses for different nodes also. Let us close this one. We can plot our results also. So contour plot, nodal solution, and we're going to see DOF solution, rotation vector sum. You can see maximum rotation is occurring at extreme right hand side node. It is 0.004973 radian, and at node number 1 it is 0 rotation, right? Next to that, we'll analyze the same problem using different types of elements. We'll consider pipe element in this case, right? So let us close this one. I will start with different element type. So file, close and start new. Do not read this one, and we'll start a new one, right? Okay. Again, as per normal practice, we'll start from preferences. It is a structural analysis, and from preprocessor we'll define the element properties. element type, add, edit, delete. Let us add this one. Instead of beam, we'll select pipe element here itself. Pipe with 3D finite strain we are considering, and element type reference number is 1. From options, we can select element behavior as hoof strain treatment, and it will be thick shell. Okay, let us close this one. And material properties, material models, structural, linear, elastic, and isotropic. It is having modulus of elasticity as 2.08 E11 and Poisson's ratio as 0.3. Okay, let us close this one. Now sections, it will not be beam as we have provided pipe. So section, we need to consider pipe. Let us add it. We are providing the pipe ID number as 1. Okay, and we are keeping the name of this one as hollow. Outer diameter was 100 mm and inner diameter was 80 mm, so it was having thickness of 10 mm only, right? So what can you do is pipe diameter 100 mm, or you can say 0.1 meter, and wall thickness will be 0.01 meter. Okay, apply. Now the second section ID, we're keeping the name of this one as 2, and the name of this one will be middle one, and pipe diameter it will be 80 mm, so it will be 0.08 meter, and as it is a solid one, so wall thickness will be 0.04 meter, right? So it is a solid one. Apply. And the third section ID, we're keeping the name of the third section ID as end, and pipe diameter is actually 0.06 meter or 60 mm. As it is a solid one, so wall thickness will be 0.03 meter, right? 0.03 meter. Okay, we have defined the different cross sections. Now we need to model it. So modeling, create nodes in active coordinate system. First node will be created at origin. Apply. Second node will be created at a distance of 0.3 meter. Apply. Third one will be created at a distance of 0.7 meter. Apply. And the last one will be made at a distance of 1.2 meter. Okay, done. So next one, we need to add these different nodes in the form of elements. As it is a step shaft of different cross sections, so we need to consider element attributes before joining these nodes into elements, right? So first of all, we'll see element attributes. It is a hollow one. The first one is the hollow one with section ID 1. So we can join this node 1 and 2 through nodes. Let us select node 1 and node 2. Apply or OK. So first element is made. Now second element, we can check it from element attributes, and section number it will be different. It will be middle one, and we can join node 2 and node 3 through nodes. Join node 2 and node 3. Okay. Second element is also made. Now the third element can be seen from element attributes. The section is actually different. It is end section. It is a solid one also. Okay. Now this node number 3 and 4 can be joined through nodes. Join node number 3 and node number 4. Okay. So we defined all the different elements with the different cross sections, right? As we have created nodes, so meshing is not required. Now we need to apply our loads, and that will come from here. It is a new analysis and it is a static structural analysis. We need to define loads, apply structural displacement on nodes. So as per question paper, first node will be fixed. Let us select node 1. Okay. All degrees of freedom with 0 displacement, that means node 1 is fixed. Okay, done. Next to that, we need to apply different moment at different locations, right? So force moment on nodes. Let us select node number 2. Apply. Along x direction, it will be having a moment of 3000 Newton meter. In anti-clockwise direction, so it will be positive. Apply. First one is done. Again, we will select the third node. Apply. In this case, it will be clockwise direction of moment 2 kilonewton meter. So it will be minus 2000 Newton meter. Apply. And the last one at node number 4, select. Okay. The last one will be 1000 Newton meter in anti-clockwise direction, so it will be positive 1000 Newton meter. Okay. We have applied all the different moments at different locations, right? Now we need to solve it. So solution, solve current LS. If everything is right, it will show solution is done. It is showing solution is done, so everything is perfect. We can see our results here, right? So close it. Now we can see our results from general post-processing. General post-processing, read results from last set, and we need to define the element table. So element table, define table, edit, and from drop down menu you can select by sequence number and it will be SMS 4, apply, and repeat the process by sequence number and it will be SMS 17. These two numbers will be representing actually torsional moment for the beam, right? Okay, update. Let us close this one. Now we want to see our results from listing. First one, we'll see the reaction solution for all items. You can see it is the same result what we got in our previous case with beam element. It is showing the reaction at node number 1 along X, Y, and Z. Not only that, we can see forces developed at node 1 along X, Y, Z direction. By the same time, we can see moments also, right? Let us close this one. Now we want to see the rotation of all the different elements that will be obtained from nodal solution and rotation vector sum. We can see at different nodes we are having different types of rotations, and all the rotations are given in radian that to be converted into degrees by multiplying with a specific factor, right? And you can see here maximum rotation is occurring at node number 4 is 0.49627 into 10⁻²⁰ radian. Okay, let us close this one. Now I want to see torsional moments that will be obtained from element table data, and we can select SMS 4 and SMS 17. Okay, so these are representing torsional moments at different elements, element 1, 2, 3. Right, let us close this one. Now the very important one, we want to see the shear stresses that will be obtained from elemental solution, and we want to see shear stress in XY direction. This is very important one. This is the most important part of our analysis. So we can see for different element, this is for element number 1, we can see stresses developed at different sections, right? First one is for section ID 1, that is for element number 1, for node 1 and node 2, and second one you can see this is for element 3, and finally you can see for the section ID 3, the last one, these are the stresses developed at different sections or different elements. Okay, let us close this one. So this is all about our today's video. This was a very simple analysis of a stepped beam under the application of moments at different locations, right? In this analysis we used two different types of elements as beam element and also pipe element, and we saw in both cases the results were exactly same. And here in this case we found the rotation of different nodes, and also we find out the shear stress developed at different elements or different sections. Okay, so thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.